So I'm starting my presentation. Thank you for introduction. I'm Hiromi Ogawa from University of Tsukuba, and today I'm going to present as Rust, a prophecy-based refinement type system for Rust. So Rust is a popular general-purpose programming language adapted across a wide range of software development fields, and it allows low-level operations for high-performance applications and system programming while ensuring memory safety through its unique type system. And in normal Rust, what we call safe Rust here, Rust type system ensures memory safety for us and by constraining pointer manipulation operations. And that constraint provides a good properties for higher level static verification. On the other hand, in code fragments that explicitly marked as unsafe, users are responsible for ensuring memory safety. So low pointer operations are permitted, and that makes such verification harder. Our work focuses on safe Rust to leverage Rust guarantees for higher level static verification. Key property of safe Rust is aliasing extra mutability. In Rust, there are two kinds of pointers. One is immutable and another is mutable. So when the pointer is immutable, there may be multiple areas of it. However, when the pointer is mutable and in safe Rust, that pointer must be the only one accessible areas. So I will illustrate that using the example, and this blue circle shows that the variable is accessible. So in this first line, a new memory location is allocated by box new call, whose content is integer 2 and it is bound to variable x. In the next line, we make a new mutable reference to the content of x, and it is bound to a variable m. Here, you can see that permission is temporarily transferred from x to m. This is what we call mutable borrow. And since m has the permission now, we can make an assignment to m updating its value, while touching x is disallowed here. Then, after the usage of mutable reference m ends, the permission automatically returns back to x, and that allows us to assert on the value of x. So this is the intuition of aliasing extra mutability rule. And because of that, if we try to update m after the last line, it is not allowed and rejected by compiler because x is also accessible here. So this property is higher level static verification of functional correctness in Rust because it reduces the scope of pointer aliasing. And various static verification tools have been proposed leveraging this property. And this table is a summarization of our evaluation of other tools. And automated dimension means the tool can infer inductive invariants automatically. And modular means it can divide verification into smaller tractable parts. And precise means it can track state change via pointers precisely. And there are also dimensions for some language features. So as you can see from this table, despite their individual strengths, now the tool provides a balanced solution that addresses all these dimensions. To fill this gap, we present as Rust, a new static verification tool for Rust that is designed to be a comprehensive solution in terms of all these dimensions. So for this design goal, we integrated refinement types, flow sensitivity, prophecies, and CHC solving, each of which I'll explain later. For the 4 dimensions I described earlier, refinement types contribute to modularity and language features. Flow sensitivity and prophecies are essential for the high precision. And CHC solving contributes to powerful automation. So let's take a look at individual ingredients. First is refinement types, which is types qualified with predicates. And as you can see from this example, this is a dependent function type. You can specify a pre and post condition of the function type, enabling verification of functional correctness. Also, refinement types contribute to supporting various language features and modular verification. Also, automatic inference of refinement types are studied, so functional correctness verification via refinement types can be automated. However, modularity and automation are in trade-off relationship. So you can see from the left example, this is a full automated for program verification that only takes input program at once and verifies it at once. And it doesn't take use the annotation. So it can be problematic and often result in timeout if the input program is large. However, on the right, you can see a modular but semi-automated verification. So it requires users to give an annotation on every single function in the program. So this makes verification problems smaller and tractable, but that simply writing annotation is tedious for users. So actually, Rust is not only modular, but takes a good part of both approaches. Because refinement types works as a verification boundaries, making verification modular, but also refinement types can be omitted if user wishes, and let Rust can infer these types automatically for you. So refinement types works as a flexible boundary of verification, striking a balance between automation and modularity. And also, Rust accommodates higher order functions and algebraic data types thanks to refinement types. So both features are essential for practical Rust programming. What about mutation? So mutation is also essential feature in Rust programming, and we want to track the effect of mutation precisely in our type system. So let's see how that works in refinement type system. This is the refinement type of variable x, and that essentially says that the content of x equals to an integer 2. And in next line, we want to update the value of x. But this does not type check naively, because simply variable 1 is not compatible with value 2. So what about giving a more relaxed type like this? So star x equals 2 or star x equals 1. So this can indeed type check this assignment, but this cannot discharge the assertion on the last line, because this type system doesn't know the exact value x has even after this assignment. So this is imprecise and also not what we want. Actually, we have to update the type like this after the assignment, and this makes our type system flow sensitive because the type changes over the course of typing. And also this kind of type overwriting is called strong update. But naively supporting strong updates can easily lead to unsoundness. So let's say example, on the right you can see refinement types. And in the next line, we create a new variable v that has a value of the current x. And then we make a strong update. So here, as we discussed before, the type of x destructively update to be a box of 1. But this confuses the type system. On the last line, we have an assertion assertion about the value of v, but this fails in runtime. But this type system concludes incorrectly that this assertion holds because of this strong updates. So this is a challenge, and we have a solution in Rust type system, and we separated the typing context. We have two typing contexts in our type system. First is place context, what we denote as delta, that binds program variables. And second is typing context, which we denote as gamma, that binds immutable snapshot of program variables in delta. So it's important to note that program variables are not bound in gamma, so first we have to bind program variables in delta. So let's see that in example. First, we have an on pointer and bind that to variable x, and it is bound in delta. Here, the logical representation of the value is bound in delta, and its inner snapshot, the immutable part of that representation, is bound in gamma, along with its refinement. So it says that the x prime is the freshly allocated variable, and its value is 2. In the next line, we create a new variable v, and as we know, the current value of x equals to x prime, we just bind x prime to v. And then we make a strong update. But that happens on delta, not in gamma. So here, content of x is replaced with x double prime. It is another freshly allocated variable, but the refinement in gamma does not change during the course of typing. So that preserves the logical meaning of v during typing, and this system can successfully reject the assertion on the last line. But we have another challenge. So this is mutable references. Mutable references are also essential for practical Rust programming. But we need to propagate change made through references to their owner to support mutable references. In this example, we have a mutable reference m that points to x, and in some way, this type system has can give a type m to that equals to 2. And in this next line, we call decrement function that decrements its argument by 1. And so suppose that this system can in some way give a type m to be decremented 1, time equal 1. But so this can successfully discharge this assertion about m, but we also have an assertion on x, and according to the aliasing between m and x, the last line, the assertion will fail in runtime. But since we didn't change the type of x, this system incorrectly concludes that this holds, so this is unsound, and we have to deal with this. So this is actually very challenging because we didn't even have any occurrence of x between this mutation and this read. So we have to propagate the value this way, backward way. So this is where the prophecy comes into our type system. Prophecies are no way to reasoning about future states, and several large verification tools have adapted prophecies for their own verification, and similarly certain incorporated prophecies to handle mutable references. Still, we need to adapt that idea because Thrush is type system-based formalization, while the prior work, RustHorn, is not. So this is the representation of mutable references in our system. So this is just a pair, and the first one is the current value of the owner, and the second one is called prophecy, and it is the future value of the owner, and also it is the final value of the reference. And we denote this first one using a star operator and the second one using circle operator. So this example is a decrement function that decrements its argument, and that effect is expressed on the return type of this function. So here this return type asserts that the prophecy of m equals to the value of m on the entry of call minus 1. So this is the effect of decrement function. All right, so let's see how this works in the typing environment. So this, as always, we bind a new Unno pointer in respective environment, and then we create a new mutable reference. And here, our type system freshly allocated a new prophecy variable, which is named L in this example, and use that to link owners and references. Owner is x here, and reference is m here. Here, so we replace the current value of inner value of x with L, and we use L as a prophecy of m. So this means that if when we use x after this statement, according to last borrowing rules, the reference m must have already been expired. So the value after that happens, the value of x after that event must be the last value of m just before the expiration, and that's exactly what prophecy means here. So let's see how this works. In the next line, we call decrement function on m, and we get new assumption from its return type. And by substituting its parameter using parameter with its argument logical representation, we get this term and can be reduced to this term. All right, and then our system can successfully discharge the assertion on the current value of x thanks to prophecies. So because star x, which is the current value of x, equals to L, and L equals to x prime minus 1, we know this assertion certainly holds. Okay. So this is the overview of our type system, and we prove the soundness of our type system under the property named well-borrowedness, which is the formalization of aliasing extra mutability property. And the important thing is that our formalization does not depend on any specific implementation of barrel checker. This design accommodates future version of the last barrel checker. And we have to talk about automation. So we adapted a non-CC-based refinement type inference method that works in 3 steps. First, it generates a template of unknown refinement type using a predicate variable, and then generates a constraint that the predicate variable must satisfy in the form of constraint horn clauses or CHCs, and finally give the constraint to the solver and let the solver solve them. And we get this kind of complex refinement type, and we don't have to write this kind of complex type but Rust infers that automatically for you. And also, Rust really utilizes CHG solving to automate reasoning about pointers, loops, or recursive function at once, thanks to our use of prophecy variables. So next is evaluation. So we conducted 2 experiments using 2 benchmark sets to check whether Rust has achieved its design goal and to compare Rust with other competing CHG-based Rust verifier. For the first benchmark, we created a new benchmark set to compare a broader range of Rust verifiers. And this is a summary of results. And in paper, we have 32 results, and this is the extraction. And in summary, this shows that Rust has achieved its design goal. So we have some example of the benchmark cases, and this shows the precision of Rust over the existing tool. And this shows this in this example, Rust performed better than the existing Rust verification tool. And also, we conduct a performance comparison against the RustHorn, the prior work, and using a RustHorn benchmark set. And as you can see from this scatter plot, verification with Rust was completed in a comparable time with RustHorn. But there are also slower cases, but we analyze that in paper, and this is our future work to address these slower cases. So that's all my presentation, and I'm happy to take questions. Thank you.
Okay. We can take questions from the audience.
Hi.
Hi.
Oh, sorry.
We're going to start up here first. Okay, thank you. Thank you for the talk. So I was curious about your prophecies. What's their connection with like post conditions in general?
Thank you for your question. Prophecy is a post condition is in general shows that prophecy is for like a post condition for mutable references. So prophecy shows the future state of mutable references, and it can be used to specify post condition of its parameter. Is it make sense?
Yeah, we can also talk later, but thank you.
Yeah, thank you.
Go ahead.
Hi, Derek Dreyer, Max Planck Institute. Very interesting work. So I have a question about the comparison with the refined Rust, actually. So refined Rust, as you know, as you cited, is also a refinement type system based on prophecies. And the type, when you showed the typing rules, I don't know if you can go back to the slide on where you were showing the typing, presenting the typing rules was a way. Basically, this part. So this felt very similar to how this would be type checked with refined Rust. So I was wondering if you could compare more technically, like what is the technical difference? I mean, I understand the automation is completely different. It's much more automated than refined Rust. But I'm wondering what the technical difference is in the type system itself.
Okay, thank you for the question. So first of all, refined Rust and Rust differs in design prophecy, design philosophy, but in detailed type system, I can't say much about the technical difference between type system. But one thing I can say is that refined Rust can handle unsafe code by lowering them to separation logic. But our system is not. We just handle safe Rust, and I think that also contributes to powerful automation. And automation is, as you said, the core difference between refined Rust and Rust. So, yeah. But we can discuss that later. Thank you for the question.
Okay, thanks.
Okay, we have time maybe for one more question. Yeah, we could try and get to both of them, but.
Hi, Ralph Young, ETH Zurich. Thanks a lot for the talk. Always nice to see more Rust verification. I was a bit surprised by your mention of stack borrows. So I wondered stack borrows doesn't do anything for nested references, right? It only really cares about the top level reference. So it seems like not enough to assume stack borrows if you want to actually have a type system where I can nest references arbitrarily. Like what do you do with nested references, and how does that relate to what stack borrows does with nested references? I'm a bit confused there.
So you mean that stack borrow is not enough to say handles listed reference in type system boundaries. So yes. Sorry. So let's discuss that later. But
yeah, let's follow up. There's a lot of interest,
really
but it's lunchtime,
question.
so let's thank our speaker one more time.